Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Aarran Shaw with us today. Hello, Aarran.
Hello. Hey,
And,
nice to be here.
oh, well, thank you so much for agreeing to talk about your very lovely article, which we'll get to in a second. Let's see. And it is February 11th of 2025 as we record this. And Aarran, what is your geolocation? Where are you at?
I'm in Indianapolis, Indiana. I'm at Butler University, a small private university just north of the city center.
Yeah, they have kind of an infamous basketball team, if I remember
Yeah,
right.
that's right, actually. Yeah.
I think they made a movie about it.
Yeah.
Very cool. So is spring in the air in the Midwest there in Indianapolis? Or are we still kind of in our winter mode?
It's still in winter mode. It's actually the weather is not fantastic at the minute. I'm really not enjoying how cold it is. But hopefully, coming around the corner, the weather will get a little better and things will start looking up. I hope so.
Yeah, yeah. It is looking up, and the corn will begin to grow in Indiana again. Great.
Yeah, yeah, absolutely.
Very cool. Let's see. And Aaron, what do you like to do for research?
Yeah, I mean, I study accretion really in all of its forms, in most of its forms, I guess. When I did my PhD, I was mostly focusing on black holes, but as I kind of went through my many postdocs, I started to explore, white dwarfs,
Hmm,
accreting neutron stars, things like that.
cool.
Anything involving a dead star, I'm interested in it.
Nice.
Yeah, yeah,
Beautiful.
yeah.
All right. And that is going to bring us to this very awesome AJ article.
Mm.
It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
Yeah, please do.
Yes. Calibrating the clock of JWST. And Aaron, take us away.
Yeah, well, thanks again for having me on. I'm really, really excited to talk about this paper. I gave a short talk about it at the AAS earlier this year,
Oh, yeah.
but this gives me a bit more of a chance to kind of expand on it in
Exactly.
more than the 5 minutes than you get for a AAS talk. So,
Exactly.
yeah, yeah. So this is a paper that was published earlier this year, and as you can see immediately, there's a whole bunch of co-authors that I'd really like to highlight here. This was a massive collaborative effort, as many of these kinds of things are. In particular, in that first line, David Kaplan, Poshak Gandhi, Tom Macro, and these people were absolutely crucial to getting this paper out. So I really, really want to thank those guys for all the support. And then, of course, there's a whole bunch of other people there. I can't shout them all out by name, but yeah, really, truly a collaborative effort. And the title, though short, I think is a very, very important aspect of this new JWST era.
Hmm.
And so, yeah, the paper is called Calibrating the Clock of JWST. And well, what might that involve? Why is that important? I guess
Cool.
that's what I'm here to tell you.
Cool. Good shout out.
So,
Okay, let's go.
yeah, so JWST, for, everything it was built for, one of the things it wasn't built for was high precision, high time resolution observations of high time resolution phenomena, right? And when I say that, I mean things on the, I guess, sub-second variability timescale.
Hmm.
So everything varies. That's what I like to think anyway. Everything in space varies. You might think it doesn't, but it does.
You just have to wait long enough.
Yeah, you just have to wait, yeah, a certain amount of time, right? And so, things can vary on days to weeks to months to years. We're talking AGN, for example.
Yes.
And then things can vary on, as you can see in the first paragraph there, in terms of nanoseconds, right? So, the Crab pulsar has nanosecond sub-pulses in between its regular millisecond pulses, et cetera, et cetera.
Uh-huh.
So variability is, as it says there, ubiquitous across all astrophysical phenomena, right?
Yes.
Um, One of the regimes that is, relatively understudied, in particular at infrared wavelengths, I would say, is the
Yeah.
sub-second regime. We have accreting compact objects like black holes, neutron stars, white dwarfs even, can show stochastic variability over on timescales less than a second. Uh, I saw some very, very interesting stuff about resolving kilometer level features in Kuiper belt objects by
Oh,
their occultation of distant stars, which is
cool.
something that I personally
Oh,
have
cool.
no knowledge about.
Yeah, very cool though.
Yeah, really, really cool. In fact, there's
Wow.
some stuff on rings being
Oh,
measured.
yeah. Uh-huh.
Yeah, it's
Hmm.
absolutely crazy. I don't know how you manage to find this stuff. But the point is, these occultations of distant stars, for example, they last, seconds or less than seconds because it's a very tiny object passing by a very distant star, right?
Yep.
So these kinds of things, pulsars, they're cosmic clocks, there's all sorts of things that are important on this sub-second time scale,
Uh-huh.
right? And to get a sense of these kind of phenomena, to really, really dig down into these phenomena, we need to have uh, accurate measurements of those, features, those timing features, right? Those flux variability or whatever it is, right?
Time
So we
domain.
need accurate measurements. Well, we need an accurate clock,
Yes.
right? To make sure that the time that we read off of our instrumentation is actually correct,
You're
right? And
correct.
how accurate it is. And the reason I brought JWST into this is because the mid-infrared regime, in particular, is really, really understudied in this kind of sub-second level, right? At this sub-second level, sorry. It's mostly due to the kind of lack of available instrumentation. JWST is sort of a successor in that way to Spitzer, I guess.
Yeah. Yeah.
Yeah, I mean, looking in the mid-infrared, I'm talking about really. Um, and it wasn't designed as a timing mission.
Right.
I'm particularly interested, by the way, just as a side note, in jets from black holes, X-ray binaries, things like that.
Uh-huh.
So, we have stellar mass black holes and neutron stars form an accretion disk when they're in an orbit with a binary companion, and sometimes, those accreting objects shoot out these highly relativistic jets,
Yep.
and we don't understand them fully. And sometimes you see
Yep.
these jets varying on crazy, crazy short time scales, right? And the spectrum uh, often kind of breaks in the mid-infrared, right? And so if we can use JWST, for example, to study these jets on excuse me, at high time resolution,
Good.
then that would kind of break open this new regime, right?
Very nice.
So this is why we sort of did this calibration experiment.
Nice.
So yeah, if we want to open up the mid-infrared regime, not just for my purposes, but for other purposes as well, everyone else's purposes,
Absolutely.
we need to know the accuracy of the clock. And it wasn't designed as a timing mission. It was designed to look at the farthest away galaxies and
You can little red
study,
dots. Little red.
yeah, little tiny red dots where you get a couple of photons and learn things about incredibly high redshift phenomena,
Yep.
which is awesome. And I absolutely commend how successful JWST has been. It's also designed to look for the building blocks of life in eclipsing planets. And I really love that idea that you can just stare through the atmosphere of a planet that's being illuminated by the star behind it. I love that stuff.
Yep. Very
But
cool.
yeah, it's really cool. And so these are all incredibly noble goals, and JWST is excelling at what it was built for.
Yep.
But it wasn't designed for doing timing studies, but we think it can be used for timing studies.
Nice.
So it was launched with a pre-launch accuracy, clock accuracy of zero point 0.5 seconds, which is fine, but let's see what it can really do.
Yeah. Okay.
Yeah, so that was the kind of motivation behind this experiment, right? So
Very.
our idea was that we would take JWST and point it at some kind of natural timing calibrator,
Okay.
something that showed very well-known timing phenomena, whether that's eclipses or pulses or something like that. And so we chose a double white dwarf binary
Ooh. Okay.
with an extremely fun long name. ZTFJ 1539 is what I'll call it here.
Yeah.
Um, and what this is two white dwarfs in a binary orbit. They eclipse, right? And they eclipse every 6.9 minutes or something crazy short like that. Yeah, the orbital period is 6.91 minutes, right?
Okay.
So very, very quick,
Yes.
very, very compact system, right?
Hmm.
And these eclipses, they occur whatever wavelength, right? You have a white dwarf eclipsing another white dwarf. So those eclipses are going to occur exactly the same time. At least the base of the eclipse is going to occur exactly the same time. This is
Uh-huh.
almost a 90-degree binary, almost anyway.
Very cool.
So those eclipses, those primary eclipses are very, very deep. They happen at every single wavelength we've observed it at. And so if we can take the very well-known ephemeris that we've measured on the ground,
Okay.
observe it with JWST, measure those eclipses, and compare the time at which JWST tells us those eclipses are from its onboard clock.
Okay.
Compare it to when we think those eclipses should have happened
Yeah.
based on the ground-based ephemeris. One number minus the other is essentially the accuracy of the clock of
Okay.
JWST.
I'm with you. Hmm.
Yeah. So hopefully that makes sense, right?
Yep. I'm with you.
Um, and so this equation here, equation one, basically informed the length of our observations. It essentially tells us what the, excuse me, essentially tells us what the uncertainty in determining the time of that binary conjunction, the eclipse is based on a couple of parameters, not least the number of samples you obtain during the eclipse, how deep the eclipse is, for example,
Yeah.
and the uncertainty on your flux points as well, right? So these are the main parameters that determine
Okay.
how to dig down into the timing accuracy that we want, right? So we want sub-second, and that motivated our long stare with JWST. So
Cool.
if we go down to table one, just for a
Sure.
second there,
Yeah, yeah, yeah. No, this is where we're
this
at.
tells us our total exposure times here,
Mhm.
right? So we did two epochs using NIRCam, the
Okay.
near infrared instrument on JWST. You might wonder, well, we're interested in the mid infrared. Why are we using NIRCam? Well, ostensibly, all of the instruments share the same clock, right?
Yes.
So,
Yes.
so we just want to gather as many photons as possible to perform this experiment, right? And
Okay.
then we can say that the accuracy that we get, that we fit or that we calculate from our near-cam results can be applied to all instrumentation on onboard JWST, right?
Fair enough. Fair
Yeah,
enough.
so this table here just shows us the when the observations took place, the filters that we used. NearCam has two detectors on it that can observe simultaneously. So there's the
Good.
short wave band, and then there's a long wave band. And you can see the average intensities we measure there, and the signal to
Hmm.
noise is in the right as well. So that's the signal to noise for a single integration as well. So each point has a signal to noise of at least 12, right? So
Yes.
that's pretty good.
Yes. Very good.
Um,
For our timing.
okay, so
Very
yeah, this kind of formed the basis of our experiment. We observed it at two epochs. Why did we observe it at two epochs? Well, we wanted to see if the clock drifted as well, right?
correct. Yes.
Um, yeah, so that makes sense. We observed in the subarray modes. So sub 160p was the subarray mode. A
Okay.
subarray mode literally just means that you take a small stamp out of the full CCD and you only read that bit out, and that
Oh,
means you have higher time resolution for downloading it. Sorry, for reading out your data.
aha.
Um,
Okay. Okay.
yeah. Um,
Learn something.
I could explain anything if you have any questions, by the way. But that was generally we were only interested in one source. And we're interested in as high time resolution as we can get, and so subarray mode makes sense, right?
Hmm.
For us. So yeah, we did these observations. We used the excellent FOT utils. Shout out to FOT utils. It's a really comprehensive Python package.
No.
You can do any kind of photometry on there. I taught an entire class, astronomical techniques class last semester using FOT utils. So yeah, Bradley et al. That's the latest version there.
Great
Thank
shout
you,
out.
Larry. Um, yeah, and then we also use the WebPSF Python package to generate PSFs for our PSF model PSFs, which we then used FOTUtils to fit to the data that
Yeah.
we had on hand.
Yes.
Okay,
Hmm.
um, and that allowed us to fit the flux for each integration.
Yes.
There's also I guess I should show figure one. Sorry to make you scroll down a little bit more, but I
Oh,
should
good.
show figure one
Oh,
just to
good.
show that
Okay, let's
So
see.
here we go. Here's figure one.
Let's fix.
So all this shows, it's not a hugely important figure in the context of this paper, but all this shows is, we fit the position, the centroid position of the
Yes.
source for each integration.
Yes.
So that's a
Our
lot of
graphic.
integrations.
Hmm?
And all this shows is like the best fit X and Y pixel centroid. And you can see from these figures,
Pretty good.
even, yeah, it's beautiful, right? This is down
It's
to the
pretty
sub,
good.
it's stable down to the sub pixel level, right?
Yeah, that's
So,
awesome. All right.
yeah, so that's all we're showing there.
Okay.
But
I'm
this
with
allowed us to also conclude that, any issues that might have arisen or any inaccuracies in the timing solution we came up with weren't down to any pixel to pixel variations of the source on the detector. So it was
excellent.
important to show the stability of the location of the source. Right. So that's
Mhm.
what figure one is. Takes up a huge fraction of the paper and is not the
Not the money
is
shot,
not
but it's an
not
important
the
shot.
showstopper here, unfortunately. But I like this figure. It took me a while to make. So,
Oh, very good. Cool.
okay. So where were we? Oh yeah. So we were extracting fluxes,
Yes.
and then
Yeah.
we end up with a light curve, right? We end up with a light curve for each filter. The two filters we used in Epoch 1 were
Yes.
F070W, which
Yes.
is centered at 700 nanometers, so a red filter.
Yep.
Um, I guess closest to I-band, I would probably say, right, ish, between
Okay.
R and I.
Yeah.
And then in the longer wave band, we used F277W. So that's your kind of near infrared filter, 2.7 microns centered, I guess.
Mm-hmm.
Then in the second epoch, you'll notice that we changed that long wave band filter.
Yeah.
And the only reason that we did this was because, well, we just wanted to gather as many photons as possible to get
Bravo.
as accurate a timing solution as possible. We'll see later that that actually became a bit of a problem.
Okay.
Uh, so
Yeah.
that's all that was. And you can see the increased signal to noise in the right of table one there for the
Oh,
F3.
yeah. Very nice.
This
Uh-huh.
is a F322W2 is just a really wide band filter,
Yes.
covers a large fraction of the near infrared. And so that's why we switched to that one. Gather as many
Mhm.
photons as we possibly can.
Cool. I'm with you.
Okay, so where do we get to? We've extracted fluxes, we've made a light curve. Okay, so in order to quantify how accurate JWST's clock is, all we need to do is fold those light curves,
Yes.
right,
Yes.
on the known ephemeris. The known ephemeris, which is there on the right hand of the right hand part of the screen there.
Uh-huh.
That T0 just refers to the time of the maximum eclipse, the
Lots of
orbital
significant
period
figures.
there,
Yeah.
and the orbital period, the p dot, right, the change in orbital period, which is very, very tiny but measurable.
Yeah. Well, there's a lot of significant digits on those numbers. So.
Yeah, yeah, I know. I'm really impressed. So that was shout out to Kevin Burge for that one. He's
Okay.
also a co-author on this paper. Kevin Burge is the guy who discovered this source,
Yes.
and is obviously responsible for, us using it as a timing calibrator. We wouldn't have known about it if it wasn't for him.
Nice. Yay.
And yeah, he gave us those ephemeris.
Mm.
So we have a light curve. We fold it on these known ephemeris,
Yes.
and then we fit the light curve, uh, mostly focusing on the difference between T naught as measured by JWST
Yes.
and T naught as written down there. Okay, and
Okay.
you can, as you said, the significant figures there are enormous. So that T0 is known very, very well.
Okay. So we're going to be using the ISIM clock. Yeah.
Oh yeah, sorry. Yeah, there's a couple of known sources of clock error as well, and this I found this out due to submitting a ticket to the JWST help desk. Shout out to the JWST help desk because they were very, very helpful in all of this.
Yay.
Um, so yeah, there's a couple of known errors, right? So the ISIM clock, the ISIM is the actually I think I defined the acronym down there. Maybe I don't.
Yeah, here it is right here. Integrate.
Yeah, the Integrated Science Instrument Module. That I believe, and
Yeah.
people can correct me if I'm wrong, that's the clock that goes to all of the instruments, right? That's the instruments read their timestamps from that clock, right?
Yes.
Um,
Yes.
that is updated from the spacecraft clock every 64 milliseconds. So if something happens within those 64 milliseconds, you can expect a maximum offset of about
There you
64
go.
milliseconds from the spacecraft clock there.
Okay.
Time between ground station contacts is variable,
Yes.
depends on many factors, but they last between 2 to 6 hours. A clock reset happens then.
Okay.
Spacecraft clock is known to drift. The drift is required to be kept to less than 42 milliseconds per day. And finally, the timestamps that are assigned to the FITS extension may vary from the end of the readout time. This is due to,
Yeah.
transfer
Yeah.
times, essentially,
Yeah.
readout times and things like that. So that's on order of 10 milliseconds.
Okay.
So you add all that up, and you're looking at maybe a maximum difference expected of 116 milliseconds between
Okay.
what JWST tells us and the reality, right?
All right.
That's what we're kind of expecting there. Now, none of this
Oh, pretty good.
is officially like, we're calibrating this to find out how close to this we really are, right?
Yes.
Um,
Yes.
excuse me.
All
So
good.
we take our light curve, we fold it on that ephemeris, we
Yes.
find the difference between T naught and T naught measured by JWST, and this hopefully gives us an idea of the accuracy.
There you go.
Okay, so
Cool.
if we scroll down a little bit,
Sure.
take a look, we've got figure one, we've dealt with figure one. Okay, so here we go. So we used a package called ELLC,
Mm-hmm.
right, to fit a model to the light curves, to the folded light curves. This is a pretty well-known modeling package, Python package that has been used for, binary stars. It's been used for eclipsing exoplanets, things like that. It's a relatively famous piece of software.
It is.
Um, and if we go down, we can see in
Okay.
figure two.
Stick with figure two. Light
Here
curve.
we go. Here's figure
Yeah.
two. This is our epoch one light curve. And we can see on the left the short band one, F070. And on the right, we see our long band one, F277W. Yeah. And we can see a very beautiful light curve
Yeah, it's quite
in
deep.
blue and in red. And we can
Mm-hmm.
also see a model that we fit to it,
Mm-hmm.
right? And those models look pretty good, right?
Pretty
Maybe a
good.
couple wobbles around the eclipse, but we used a Monte Carlo technique. Probably won't show the corner plots unless you really want me to later, but basically there's a whole bunch of wavelength dependent parameters like gravity darkening, limb darkening
Yes.
coefficients,
Yes.
things like that. But the one thing we really, really care about is the time of that eclipse.
Yes.
Okay, that's the one thing that really matters here.
Mm-hmm.
Of course, gravity darkening, limb darkening, and radii of the companion star and stuff like that. That all matters.
Sure. For sure.
But these are already relatively well. The binary parameters, at least, are very well known.
Yes.
We only really care about the T0. Okay, so that's kind of what we're focused on here. I really probably won't focus on the wavelength dependent parameters much longer.
Okay. Yeah, because we're really about the timing here. So, okay.
Yes.
So
Okay.
they.
So yeah, we perform that fit to both epochs. You can see if you scroll down a little bit, you'll see the same figure, but for the second epoch of JWST
Okay,
data. So
let's take a
figure
look at both of
three.
them.
Yeah.
And
I guess the
good.
formatting put this on a separate page,
Okay.
which is fine, which is
All
totally fine
good.
by me.
It's fine. I'm with you. Yeah, the
Yeah,
residuals look good,
yeah,
but it looks deep.
yeah. So
Deep.
that's the key point there, right? It's a really nice deep
Yeah.
eclipse, right?
Deep
So
clips. Right?
enables us to perform these kind of measurements. Right?
Mm-hmm. Mm-hmm. Perfect. System.
Okay, so if we go back up a little bit.
Mm-hmm.
All
And
right, so here we go. Just stop there a second. In epoch one, we find a difference between T0 as measured by JWST and T0 as measured by our very well-known ephemeris, right?
yes.
The difference is about zero point zero 0.08 seconds, plus or minus 0.07. That's fantastic. That's really, really
Very
good.
good.
That tells us that's on the order of what was maybe expected from the known source of clock error.
Just for reference to get that back up in my head.
It's about 160
Yeah, so there's
milliseconds.
about, 60,000 milliseconds, and we're getting it agreement down to at least five significant figures. So that's six significant figures. That's pretty good.
Yeah, we did pretty good. We were very, very happy with Epoch 1.
Nice.
In fact,
Hmm.
yeah.
Hmm.
So that immediately gives you an idea of how accurately you can do timing with JWST. You can do sub-second timing.
Yes.
Now we can look at sorry, not figure, Epoch 2, and it's probably up just a little bit there in the second column.
Yeah, Epoch
Yeah.
2. Right.
So just up a tiny bit more.
Oh, sorry. Oh, here we go. Sorry.
Yeah, here we go. So in Epoch 2,
Archer.
that's where the problems start. We find a much, much larger timing offset of
Mm,
negative 0.25 second. And this is nowhere near the expected maximum source of error, which would be about 160 milliseconds.
right.
So we need to investigate this a little bit further. Okay.
What's causing this?
Now, first thing you automatically check is how good are the ephemeris, right? The
Yeah.
ephemeris are excellent. You can see that from the number of significant figures. These have been checked over more than 6 years of optical monitoring of this source since it was discovered,
Yep.
using a variety of telescopes. So telescopes that have hypercam. Hypercam is a very, very high precision instrument on the 10.4 meter GTC in La
Hmm.
Palma. You can see that the timing accuracy of hypercam is like, 100 microseconds, right?
Very cool.
Um, Again, shout out to Vic Dillon, who's a co-author on this paper, and he's one of the key kind of minds behind hypercam.
Nice. Good.
Chimera as well, which is at Palomar, absolute
Mhm.
timing accuracy. So the point is, the ephemeris are good; they're golden. It's
They're
very,
good.
very unlikely that the difference that we measure is due to some inaccuracy in the ephemeris, right?
Yes.
So
So it's not that.
sanity check, right?
Not that.
But we did, like I said, a bit of a sanity check. We took observations with Hypercam that took place at very similar times to JWST Epoch 2.
Super.
And so you can see those in figure, I want to say 4, maybe? I'm not actually 100%
Slide
sure.
down.
Oh, here we go. Yeah, figure 4.
Hypercam, yeah. Hmm.
Yeah, so there's the Hypercam observations. Right? And these are simultaneously taken in 5 filters as well, which is awesome.
Nice.
So yeah, so they've got all sorts of crazy beam splitters and dichroics going on that like enable you to observe 5 filters at a time.
That's
Fantastic.
that's
And
awesome.
these light curves look great, and there's absolutely nothing wrong with them. This
Yeah.
was taken just after Epoch 2
Uh,
and gives
okay.
us a very similar timing offset, right? Doesn't,
Okay.
yeah. So that's our sanity check. Okay. Okay. So if we go back up just a little bit, back to
Uh-huh.
our
Mhm.
text.
Let's see further investigation. Here we go.
Yep. So further investigation, hypercam, absolutely fine. Great timing accuracy. Okay, we've scrolled down a little bit. Sorry, I've made you come all the way back up here.
All good. It's all good.
Yeah. Okay, past figure 3 and 4.
Okay. There's more about hypercam.
There we go.
Go.
This is just telling us about the reduction, and when comparing them, we have absolutely nothing wrong. Comparing those to Epoch 1, comparing those to the known ephemeris. So it's something to do with JWST Epoch 2 alone.
Okay.
Um,
Okay.
all right.
Yep. Everybody's on the same time scale.
Yeah.
TDD. Yep. Mm-hmm.
So in that right-hand column there, you'll see we ended up breaking things down into the epoch. Sorry, in epoch 2, we broke it down per filter, and then we
Right.
did a fit separately to each filter. And you can
Right.
see there in the F070 band, we find delta T naught to be 0.18.
Okay.
And in the F322W2 band, we find delta T0 to be negative 0.78. Average those together, there's your 0.25, essentially weighted average rate.
Yes. Uh-huh.
Uh, yeah.
Large.
So, negative
Or
0.25.
larger, I should say.
Yeah.
Yeah.
Right. So even though the F070 band seems a little high, it's still consistent with that 116 milliseconds. So
Yep.
we can come to the conclusion that there's something wrong specifically with the long waveband filter, the F322W2 band.
Right.
Okay. So you can see that if we go down to the
Oh, here
next
we go.
figure
Yeah, yeah,
and
beautiful.
we look at this, and I think this here is the real kill shot, right? So this is just zoomed in onto the eclipse
Yes.
in Epoch 2, and we can see,
Ooh,
I think I can see anyway, but I've stared at this a long, long time now. There seems to be some kind of asymmetry in the eclipse. Can you see
yes.
that?
Yes,
Yeah.
right here. There's a little like it bounces up and then
There's a
it
little bump, but
a
also
little
the
bump.
egress is shallower than the
Oh, yes.
ingress,
Right,
right?
right. Oh,
And
definitely.
that's the real killer there, I would say.
Yeah, I mean, it's much
Uh,
deeper, much cleaner in FO7.
right,
Yeah.
exactly right.
Okay.
So this got us thinking, okay, what's going on here? There's something wrong with the eclipse. Could it be some data extraction issue? Well, we extracted all the data the same way, and Epoch 1 was fine, and everything looks fine in the F070, right?
Yes.
So
Uh-huh.
probably not a data extraction issue, right?
Okay.
Obviously, I checked everything, of course, did my
Not
due
yeah.
diligence.
So
Okay, so the only real thing there is that there's some kind of physical thing going on.
that's a positive.
Of
Yeah.
course, we statistically checked this asymmetry, right? So if we go down just a touch,
Uh-huh.
um, you'll see that we performed a time skewness test, which essentially just calculates a parameter called the time skewness statistic. There, the equation there shown in equation
Yes,
two,
yes, yes, yes.
and it
Oh,
essentially just says if this time skewness statistic is a large number, then you're probably looking at some asymmetry. Okay.
yes. Okay.
Yeah.
Mm-hmm.
So we calculate this, and that's the formula there, where S is the flux, SI is the flux of the ith element, and the sigma is your standard deviation of the flux.
Yeah.
And we only use this on the around the primary eclipses. Okay. U is a number that represents the time bin, right?
Okay.
Right. Uh, and if you go down, it's easier to just show you a figure. So if we just go down to the next figure, and then we'll come back up here later.
Sure. Let's
Figure
uh,
5 now, I'm guessing.
all right, let's go. Ooh, here we go. TS
Yes.
is
Yeah.
yep.
Spoiling the conclusion. So we performed this, and to do our due diligence, we did it on every single epoch and filter.
Yes.
And on the right-hand side, you will see in
Yikes.
Epoch 2, there
Yikes.
is a huge jump around the time of eclipse,
Yes.
and that's what those orange spikes are, compared to in F070, where that number is much, much smaller.
Yes.
On the left, those numbers are very, very tiny as well. They're on the same scale. So there's no evidence of a major asymmetry
Okay.
except in F322W2. So that's what this shows here.
Okay, I'm with you.
Okay. So that confirms it to us. There is an asymmetry,
Yes.
right? So that's what's causing our problems in the calculation of the delta T zero in epoch 2.
Okay.
Okay, so this is physical. We can't think of anything else it could be. Like, there's no data analysis issues here, no data reduction issues, because everything was done in the same way, right? It was consistent across all of the observations. Okay.
Right.
Um,
So
so
in
the only thing we can think of is it's some kind of physical mechanism, and the eclipse is truly asymmetric, right?
okay. Okay. That's
Um,
what I was getting
and
at.
so, of
So
course, when we were modeling our light curves, we weren't modeling an asymmetric eclipse, and that's what's given us the dodgy time difference there.
okay. Okay.
Okay. Now, I'm going to say a phrase that all of my colleagues, you've probably used before, everyone I know in astronomy, the source of this asymmetry was not, oh, sorry, was beyond the scope of this paper. Everyone's favorite phrase, right?
Fair enough. How many times have I seen that in a review?
Yeah. You must have written it yourself, surely.
Very good. But
Anyway,
but it's physically in the system. That is what it so it's
yeah.
really the
So we
discovery.
offer some potential ideas. So if you scroll up a little bit, we offer some potential ideas, but don't really explore them too much further.
Sure. Because as
Um,
okay.
so maybe there's
Um,
some kind of star spots on the surface, but I
okay.
doubt that that's the case. One idea that myself and my co-authors really liked the idea of is that one of these white dwarfs is maybe magnetic,
Yes.
and shows because this source hasn't been observed at these wavelengths before. So maybe there's some kind of cyclotron feature that
Okay.
appears in the F322W2 band, but maybe not in the other near infrared
Look
bands.
that up.
And
Yeah.
that's what's causing the asymmetry. So to really explore this, we would love to get maybe a MIRI spectrum or some kind of near infrared or mid infrared spectrum. That would be really cool.
Right.
But for the purposes of this work, which is solely focused on calibrating the clock of JWST,
Yes.
we use only F070 for Epoch 2, and
Okay.
we revise our measured offset to that 0.18, which is
Okay.
perhaps less satisfying, but still fits within the known sources of uncertainty on the clock. Okay.
Yep.
So in table two, which you might
Okay.
have to scroll down a little bit further, you'll see our final results for our final fits. And
And
you'll also see
two.
just the F070 figure in Epoch 2. So there you go. Table 2 tells us, and the key one, the key parameter is that top line there.
Yep.
So a lot of these parameters here are the kind of wavelength dependent parameters. And if you read the paper, you can really dig down into that if you'd like to.
And
But
see
the
the corner
key
plots.
yeah, and look at the corner plots as well. Yeah, where you can see, we measure these very, very tightly. We do a good job. Okay. One thing I did mention was clock drift, and we tried to measure the clock drift as well. And the way we did that was we split each light curve up into, I think we took 3 segments for each epoch, performed the same analysis to try and see if that delta T0 changed over the course of the
Ah.
observation to see if the clock drift.
Yeah. Yeah.
Now in Epoch 2, we've slashed the amount of data we have in half. So in Epoch 2, you can see the error bars are huge and we can't measure anything. In
Yeah.
Epoch 1, I would also say that the clock remains steady within uncertainties. Perhaps you
Sure.
can see some kind of, you know, maybe drop down to delta T0 equals 0. The gray bands here, I got to point out, is when when JWST was in contact with a ground station.
Got it.
That's when the clock is reset. And so
Hmm.
you'd expect things to move closer to consistent with 0, right?
Yes. As
But
you. Yes.
the kind of upshot of this is, splitting the data into thirds. We couldn't measure any clock drift. We couldn't measure any measurable clock drift, I would say.
Okay.
But we included it just to show this matter, right?
Completeness. Yes.
Completeness, exactly. That was in the scope of this paper.
Definitely. Okay.
Um, so I guess, I mean, the results are there for all to see. So I guess I could just conclude now, right?
If you like.
And talk about what we actually found, right?
Yes.
We found from measuring this double eclipsing white dwarf, we found that the comparison of the known midpoint of the ephemeris to the midpoint we measure of the eclipse with JWST
Yes.
is at a sub-second level. In Epoch
Correct.
1, we find 0.08 plus or minus 0.07 seconds. And in
Hmm.
Epoch 2, using only the shortwave band filter,
Right.
we find 0.18 plus or minus 0.09. Combine that for a weighted average implies a clock accuracy of 0.12 plus or minus 0.06 seconds.
Bang.
That there is our conclusion.
Bang.
Okay. And this tells us that it matches with the known sources of error that I found out from the JWST help desk, the
Yes.
116 millisecond difference. And more importantly, it tests that, right? That's
Correct.
the point here. So we actually have a testable and tested measurement of the clock accuracy of JWST.
And they're
And
consistent.
our results improve on the pre-launch clock accuracy requirement of 0.5 seconds by, a factor of 3 or so, right?
Definitely.
So, so that's important. It means we can do timing down to, let's say, around 100 millisecond level. That means we can do these experiments that I talked about in the beginning. We can do our sub-second accuracy measurements of jets in X-ray binaries. We can measure those kilometer level features on distant Kuiper belt objects that are occulting distant stars. By the way, we can find when those occultations will happen because of Gaia. So this is kind of synergy with
Yeah,
Gaia
yeah,
as well, right?
yeah.
Gaia has this like catalog of all of these things, and you can just look through that and go, oh, that's gonna occult that star at this point, right?
Yes.
And now we have JWST being able to do this. Maybe we can then move this on and measure, rings and I mean, something that I've never thought about as a person is like rings on Kuiper Belt objects, but apparently they exist. How cool is that, right?
Very cool.
So, so yeah,
Nice. Very
that's
nice.
the key kind of result there, right? The mid-infrared you've highlighted, the mid-infrared regime is
Mm-hmm.
very poorly explored in the sub-second level, at the sub-second level anyway. And
Awesome.
so now we can start to work on this. We already have started to work on this in the field of black hole X-ray binaries. Poshak Gandhi uh, uh, submitted, and the paper was recently accepted, a study of the X-ray binary GRS 1915 plus 105. We got MIRI spectra, and we can actually measure any time lags and stuff in those spectra. So I really do encourage you to check out that paper for kind of a scientific use of this calibration effort here. Um, so yeah, I mean, what
Cool.
does the future hold for this field? Well, I mean, I don't want to overstate anything. I think this work was very, very important. And you can see that we've already started using these results to study X-ray binaries, right?
Yep.
So I think in the sense of my field, I think that is like a really, really vital thing to do because it's a poorly explored area of my field, black hole X-ray binaries. Um, what can we do further, right? Well, this has opened up this infrared regime, in my opinion, anyway, to the sub-second kind of timescales. I've talked about how you can use this to, measure features on Kuiper Belt objects. I've talked about black hole X-ray binaries. What I'd really like to do is revisit this experiment with other instruments. I mentioned close to the beginning that all the instruments share the same clock, right?
Mm-hmm.
Um,
Yep.
I would like to test that, right? The idea is you should be able to use near spec. You should be able to
Yes.
use NRIS,
Yes.
yeah, sorry, and MIRI to do a similar experiment and find the same result. But I think I'm confident that we would find the same result, but we should test that really. So that's what I'd like to look into next is can we repeat this experiment with other instruments on JWST? And if you don't find the same result, then that's something that's very, very worth talking about, isn't it?
Absolutely.
Yeah. And then the side note, we actually got some interesting science that we didn't expect out of this, in that we found the kind of asymmetry, right? The asymmetry of the eclipse,
Uh-huh.
and I really, really, really want to know what that is,
Right.
right? And then perhaps once we have an idea of what that is, we could maybe refine our results here as well, right? Go
So,
back, fit the light
like if there
curve,
really is a physical asymmetry there, you could account for that in the initial model, and the fit would
right,
have been better
right.
than what it
Yeah,
is.
so we didn't mean to turn up interesting science. We just meant to do a pure calibration, but that never works, does it? Nothing ever works the way it's supposed to. So I'm really happy that we found this result, even though it spoiled the calibration ever so slightly. I think it was an important result to turn up. So I'm hoping that we can some of the co-authors and we can work together and kind of come up with a proposal to kind of investigate this because it
Absolutely.
is really interesting. And if it's down to some kind of maybe some kind of magnetic feature, that's interesting. Cosmic magnetism's always this age-old question, right?
Where's
Where did it come from? How magnetic are these white dwarfs, etc., etc.
yes.
So yeah, there's a bright future ahead for this kind of work, and I think it's just the beginning. And yeah, I really, really appreciate you letting me talk your ear off about that.
Oh, it was wonderful. It was wonderful. It's beautiful work. It's beautiful work, Aaron.
Mm,
And I think it'll really help open up sort of time domain in the
mhm, mhm.
mid IR, and there'll
Yeah,
be lots of applications of that. So it's really cool. And
yeah.
I'm so glad you did this work.
So
Very nice.
I just want to just highlight one more thing, if that's okay. You don't need to open up the paper again,
Sure.
but in the acknowledgements, there's a dedication to one of our
Ah,
colleagues,
yes,
Tom
yes, yes,
Marsh.
yes, yes,
Yeah, who unfortunately passed away recently.
yes.
Tom was the guy who really solidified this source as the calibration source.
Hmm.
Uh, he was a giant in our field of accreting compact objects. He was also one of the brains behind Hypercam. So Tom is greatly missed, and we really do credit him with the selection of this particular source as a calibrator. We were talking about, using pulsars. We were talking about using
True.
intermediate polars. He was like, "Why don't we just use this eclipsing binary that's just been found?" And so he's there's a lot of credit that needs to be given to Tom for this program. So we miss you, Tom, and yeah, thank you for the kind of contributions to this field.
Beautiful, Aaron. Beautiful. Thank you so much for walking us through your very awesome article. And I really look forward to seeing this field develop over the next couple of years as JWST becomes a transient machine.
Yeah, thank you very much. Me too. I'm really excited. Anyone watching this, please accept my proposals.
That's fair game here. That's fair game. All righty. That'll do, everyone. And I hope this made your astronomy timing day just a little bit better. And we will see you on the next one. Bye bye.
Thank you. Bye.